Okay, welcome back. We are now on installment number 4 of the discussion of the wonderful world of plastics, specifically thermoplastics, what we've been talking about. And we left off with melt flow index, and a very, very important parameter. It determines a lot about the overall molecular weight and the molecular distribution within a polymer. As I said before, it's the most common parameter that's specified when describing a polymer because it expresses very important flow characteristics of that polymer in terms of what we call the polymer melt viscosities for all melt processable thermoplastics. Now, polymer melt is just a term that they use for describing the plastic or the polymer as it's being melted in a plastic processing machine. Obviously, it will be some kind of an extruder usually, either extrusion or through injection molding, but they still use an extruder screw to do it with. So that just describes the actual physical characteristic of the polymer. It goes from a solid to a liquid, and so they call it a polymer melt. But at any rate, that obviously is going to have different viscosities, and that's very, very indicative as to just how that particular plastic can be processed and what type of parts and what type of molds. And as I said before, when you have high values of that MFI, they indicate low molecular weights, all right, and or a low degree of polymerization. And low values in MFI means that there wasn't very much to get through that small little orifice, and that indicates high molecular weights or a very high degree of polymerization. Now, the high degree of polymerization, of course, means that you basically show an increase in the potential for mechanical strength of that polymer. But, however, like everything else, there's a compromise, and that is the fact that now it becomes more and more difficult to physically push that material due to its high viscosity through these very, very small, tiny orifices and or passages and runners into some kind of a complex part. So it's sort of a trade-off there between gaining strength and gaining low viscosity values if possible. So that's something to consider, and that's why that melt flow index is so critical when determining from a processing standpoint whether or not you can produce something with a particular blend. Okay, so that kind of wraps that up. But so we want to start now polymer crystallinity. That also is another very, very important factor that determines a lot about the polymer's characteristics and properties. Now, we're familiar with crystallinity with respect to metals. Obviously, most metals are all highly ordered, highly crystalline. And then there's some amorphous structures, but the lion's share of most of the materials we talked about were highly crystalline, highly ordered structures. But when we were talking about that, we were simply just talking about within that lattice structure, just atoms, all right, or ions, but mostly just atoms. But it's a whole other world in polymer world, because now we're talking about molecules. And recall that those molecules are easily long molecular chains. Like I was telling you, like the pull chain on a ceiling fan. Just imagine that being 100 yards long or something. So now we're trying to get those in some sort of an ordered structure, ordered state. And so it becomes much, much more complex in polymer crystallinity as opposed to metallic crystallinity. And so now we're trying to take and pack those long molecular chains to produce some kind of an ordered atomic array. And because of that, there really only exist areas of crystalline regions Those are ordered regions within generally an amorphous area. So there is no such thing as a 100% crystalline plastic or polymer. They're always going to have regions or areas of amorphous areas. And as a matter of fact, the crystalline regions, which we're calling crystallites here, usually just range anywhere from 45 up to about 95% maximum of crystalline regions, which we're calling crystallites. Now I've drawn here something a little bit of a what it kind of looks like, but this obviously is this region, a kind of accordion, kind of stacking back and forth. This is this chain that is gaining some orderliness to it, and then it goes off and starts going into more of an amorphous, just kind of willy-nilly. And then it gets back in and starts to form this ordered region. So it's these little ordered regions that make up, and why we call it just a semi-crystalline structured polymer. So every polymer will have that, and you will need to know whether or not it's a semi-crystalline or a amorphous, because there's some certain specific properties associated with that, which we'll go into here in a minute. But this is, kind of like the ribbon candy maybe you might have seen at Christmas time or something. But be that as it may, but you can also have a polymer, and many polymers are 100% amorphous in structure. Now there's some things that go along with that, but just again recognize that the more crystalline we have, the more these crystallites are going to be showing up. And they can only go to maximum about 95%. You'll never reach 100% crystalline polymer structure. Okay, so let's look at some things here regarding the structure, and specifically on amorphous structures, because transparency, which we said, polymers can go in the opacity area. It can go from 100% opaque to 100% transparent, and then we have something in between called translucency. So, and what's taking place is that only 100% amorphous structures are going to be completely transparent. All right, so any kind of completely transparent plastic that you see, like the lenses in your glasses, are going to be an amorphous, 100% amorphous structure. Now, as more and more crystallites form in some of these polymers, you start adding in a little bit of translucency. It starts to kind of cloud up a little bit, until where, it becomes, this is really high, 80 to 90%, then it starts to become almost completely opaque. So, of course, you can color anything, but I'm talking about its natural structure to it. So that's kind of an interesting factor. Now, the other thing that's interesting that hinges around this, whether it's a semi-crystalline plastic or an amorphous plastic, is something we call the T sub m, which of course you know is the melting temperature, versus something we call a glass transition temperature, or T sub g. Now, only semi-crystalline polymers have a specific melting temperature, where you can go to a chart and look up specific melting temperature of that polymer, and it'll have that specific number. In other words, because then all of a sudden what happens is, it's just like those dominoes when we had in metals. When you hit one, they all go, and they all go quickly, and so that's that melting temperature right there. So the same thing happens here, is that once these little ribbons go, they go rather rapidly. So that constitutes a melting temperature, a melting point for that particular polymer. Now what happens is, on the amorphous side, it doesn't happen, because these strands are just, there's none of this orderliness. They're all just willy-nilly like this. There's much too entanglement of all these chains, and too cluttered up, and it's impossible to get them completely untangled all at once. All right, so therefore, amorphous materials do not have a specific melting temperature. They have more what they call a softening range, a temperature range where that polymer begins to get softer, and then finally will begin to liquefy some. So there lies a difference between an amorphous and a semicrystalline with respect to a melting temperature, whether or not it has a specific melting temperature or whether it has a softening kind of a range to it if it's an amorphous. Now, the other temperature I want to talk to you about just briefly here is something called the glass transition temperature. Now, whereas the difference between a semicrystalline and amorphous, one has a melting temperature and one doesn't. All plastics, all polymers have what we call a glass transition temperature. Now that's an interesting phenomenon because it is very similar to the brittleness of the metal, the ductile to brittle transition temperature for metals, where all of a sudden the metals that were once really tough and ductile, once they begin to get cold, they become very, very brittle. All right, the same exact thing happens here in polymers, but we call it a glass transition temperature. And every polymer will have a specific glass transition temperature that you would have to be aware of, especially if you're talking about applying or designing plastics going to be in cold environments, let's say. And when I say cold environments, I don't mean below freezing. I'm talking about 40 degrees, 60 degrees, sometimes even 100 degrees. Polymers can have a glass transition temperature where they begin to behave more on a brittle standpoint than a more flexible standpoint that most plastics would behave at room temperature, let's say. So you have to be aware of every polymer's glass transition temperature, first of all, just to be able to determine what it is so you know what kind of benchmark you have. So that you don't design something that all of a sudden becomes very, very brittle where you thought it was always going to be very flexible. Okay, and what normally would be a very flexible plastic could very easily just all of a sudden tear, all right, become very brittle. So always be aware of this glass transition temperature for every polymer because they all have them. And again, some of them are very, very low temperatures and some of them are pretty high actually. So you have to be aware of those situations. Now, what we'll talk about now is some facts with respect to properties and I'm going to write these down here. As crystallinity, the amount of crystallinity in a polymer increases, some things begin to change property-wise. Okay. And so that's what I wanted to show you here. Okay, so as crystallinity increases, all right, as crystallinity increases in plastics. In other words, this starts to get higher and higher. As they increase, so does following. All right, and the first one, of course, you might suspect is the density. The density is definitely going to increase. I mean, you can see that. Obviously, I mean, much easier to pack all these orderly segments in here into a much denser section as opposed to just a bunch of willy-nilly bowl of spaghetti trying to pack all that up. So the density is definitely going to increase as the higher crystallinity percentage goes higher and higher. Okay, so that's definitely one. Here's some very important information because it's relevant to what we've been talking about property-wise when we've been over these properties, but the strength increases, not only strength, but stiffness, and you know these properties, of course, and finally toughness. All of these major material properties are on the rise as the crystallinity percentage increases in that polymer. Okay, so very important to understand that. Also has better heat resistance. The polymer has better heat resistance. And there goes the buzzer timer again. Okay, so along with that heat resistance, but also it is more chemically resistant. It becomes more chemically resistant. All right. Now, got that mixed up. Let's start this over. Resistant, okay, as the percentage increases, and this one, as we already discussed, as the crystallinity increases, it becomes less transparent, becomes less transparent. Okay, and we already discussed that because only 100% amorphous structure can have pure, true transparency. Okay, so these are some important property notes that change as the crystallinity percentage increases in that polymer. And to show you, let's go back to our wonderful polyethylene. And I told you we have a low density, let's just put it this way. We have an LDPE, and then we also have an HDPE. And let me give you some properties with respect to that. And the first one, let's just call it degree of crystallinity. Okay, for a low density polyethylene, it's usually somewhere around 55%. All right, 55% of the area is going to be taken up by these crystallites. Whereas an HDPE is going to be closer to 92%. 92%. So it's very, very crystalline over compared to the low density polyethylene. Okay, the specific gravity is also going to be slightly different. It's about 0.92 on the LDPE and about 0.96 on the HDPE. A little bit different, but they're both less than 1, of course. And now here's the one talking about stiffness right here. Let's look at the modulus elasticity. All right, modulus elasticity E for an LDPE, it's at a whopping 20,000 psi, whereas with this high amount you suspect to be greater, and it is, it's way up there to the tune of 100,000 psi. Now I know that's nowhere close to being what metals are, but again, we're talking about a completely different material here. But what I wanted you to see is the difference that it actually does make by increasing the crystallinity amount in that same polyethylene. Okay, and we're doing that by the degree of crystallinity and the degree of polymerization. How many we add in that chain? Okay, now. Let's see, it really affects, well, actually, if you look at the melting temperature, it is going to be at about, let's see, about 230 degrees here, Fahrenheit, whereas for the HDP, it'd be 275, all right? So it's a little bit higher there, too. Okay. Well, I'm running out of time, of course, as usual, but we will try to get this wrapped up on the next one and finalize plastics if we can on the 5th edition. All right.